This sample problem is in relation to our traverse computation PowerPoint. We have a 12-step process that we go through when doing our traverse computations. So this is a sample problem related to those 12 steps. We will go over the documentation and then go through each of the 12 steps. So we've run a traverse on a small job site. Attempts were made to measure angles with equal precision. However, notes in the field book indicate that the setup was at point B was hurried due to other work being completed in the same area. So remember, this will affect our angle adjustments. We have our 3 separate ways of adjusting angles. It can either be random, it can be equal, or it can be based off of our field notes. Since we already know we had to hurry at point B, there's a very likely possibility that our error will come into point B. We're given our direction of AB as an azimuth of 114 degrees, 12 minutes. Determine the linear area of closure and the precision. We need to adjust the traverse using the compass rule and perform all necessary calculations to determine the coordinates of point B and C. We are given the coordinates of point A as north 5,000 and east 10,000. We have our points and our field angles that were measured in the field, and then our distance that we ran to determine what the distance are between A to B, B to C, and then C back to A. So now we will go through the 12 steps. Step 1, measure distances and angles in the field, which we just did. So step 1, this is something we would have done in lab if we were actually running the traverse, and we ended up with our same numbers. So go back to the slide that shows our field angles and our distances. This is what we would have actually performed and came up with these numbers. So step 1, fairly simple, already done. Step 2 is adjust the angles. As I mentioned, our field book indicated that point B was hurried, so what we are going to assume is that we are going to apply all of our adjustment to point B. In order to do that, we first need to total up our numbers. So if we sum our angles from our chart, we have 26 degrees, 29 minutes, 28 seconds for A. We have 10 degrees, 0 minutes, 12 seconds for B. And C, 143 degrees, 30 minutes, 32 seconds. We add all of that up, we are given 180 degrees, 0 minutes, and 12 seconds. So what this said is we are over the 180 degrees. We have a 3-sided traverse. That means once we sum up all the angles, we should be at 180 degrees. We are 12 seconds over that. We're going to apply all of that correction to point B because our field notes suggested so. So our adjusted angles A will remain the same. B will now be 10 degrees, 0 minutes, and 0 seconds. So because we had 12 seconds and we were over, we need to subtract those 12 seconds. C also remains the same, 143, 30, 32. Step 3, determine starting direction for one of the lines. This was actually given in our problem. We are told the direction of AB is 114 degrees, 12 minutes. So this is given, AB 114, 12 minutes. Step 4, calculate the direction for all of the lines. This one will be a little bit more lengthy in step. So step 4, we need to determine the direction. Make sure here that you are working in azimuths rather than bearings. It is easier to do our calculations. And also we need to know that we are running the traverse clockwise. This is important because this determines how we are doing our calculations, whether we add or subtract. So remember, first, to get to our direction, we need to calculate a back azimuth, and that is equal to our forward azimuth plus 180 degrees. Since we are running our traverse clockwise, that means we need to subtract our adjusted interior angle from our back azimuth. So what that means, our adjusted interior angle are what we just came up with in step 2. So these are the ones we're going to be using, not our original ones that we measured in the field. From here on out, everything will be based off of our adjusted angles. So we need to start using our forward azimuth that's given to run through all of our calculations. Important note, if your direction ends up being greater than 360 degrees, that means you need to subtract 360 degrees. There's 360 degrees in a circle. So if we're looking at running our direction, if we're going around and we get all the way back to 360 degrees, and we find out that this is actually going a little bit further, and we end up with something that, for example, is 370 degrees, it means that we need to subtract out 360 and end up with just 10 degrees. 10 degrees and 370 degrees are the same thing when it comes to our direction. Now, be careful. Do not subtract if your back azimuth is greater than 360 degrees. Back azimuths are allowed to be greater than 360 degrees. Directions are not. So in your steps, if it is greater than 360 degrees as a back azimuth, you're fine. Once you subtract out your interior angle and end up with your direction, if that is greater than 360 degrees, then you will need to subtract. So we're starting with AB as 114 degrees and 12 minutes. This is our forward azimuth. Therefore, we need to add 180 degrees to get our back azimuth. 294 degrees, 12 minutes is our back azimuth. We need to subtract our interior angle. Be careful here because we're going clockwise. That means we're going A, B, C. So when we subtract our interior angle, the first angle we need to start with is B. So we need to take our 294, 12, and subtract out the adjusted 10, 0, 0 as our interior angle. This is not our A angle. We start with B because we're moving around our traverse. That leaves us with 284 degrees, 12 minutes. So that is our direction for BC. All right, so it is not greater than 360 degrees, so we are fine. Moving on, we continue with what we have just calculated. We use 284 degrees, 12 minutes. This is our forward azimuth for BC. So we add 180 degrees, and we end up with 464 degrees, 12 minutes as our back azimuth. And again here, this is a back azimuth that is over 360 degrees. We do not subtract our 360. Back azimuths can be over 360 degrees. It is our directions that cannot. So once we subtract out our interior angle in our next step, our 464, 12, minus our 143, 30, 32, we will end up with 320, 41, 48. So this is our direction for CA. Less than 360, so we're fine. At this point, we do have all three of our directions. We have AB, we have BC, we have CA, but it's always good to go back and check and make sure that we are doing our calculations correct. In order to do that, we just simply close the loop. We use our 320, 41, 28, add 180 degrees to get our back azimuth, and we end up with 500, 41, 28. We subtract our interior angle, so this is where we will be subtracting out our A angle, which is 26 degrees, 29, 28. And that will get us back to 114 degrees and 12 minutes. Now you might notice something here. We have 500 minus 26. So how does that equal 114? Well, it doesn't. What it does equal is actually 474 degrees and 12 minutes. But because this is a direction that's greater than 360 degrees, if we subtract out our 360 degrees, we will be left with 114. So, skipping a step when writing it out, but it is showing that yes, we do need to subtract. The 474 and 114 are the same angle. If you are looking to convert your degrees, minutes, seconds to decimal, to do that in your calculator, say for example, we are using 320 degrees, 41, 28 from direction CA, just as an example. If you want to put that in decimal, what you would need to do is divide 28 by 60, because there's 60 seconds in a minute. Add your minutes to that. Then take that entire number and divide that by 60, because there are 60 minutes in a degree. Take that number and add your 320 degrees. At that point, it will put it in a decimal. It would be 320.6911, and we just leave it in degree. This will be beneficial from here on out, so you don't have to type in your degrees, minutes, seconds if you convert everything into decimal. If you do it in a spreadsheet, it will automatically do it for you. Moving on to step 5, determine the trig functions of the directions. So this is where we're using our sine and our cosine, depending on whether or not we are dealing with our latitude or departure. All right, so step 5, we're looking at our trig functions. So here we use the directions we just calculated for each one. AB 114.12. BC is 284.12, and CA 320, 41.28. And again, if you put them in decimal, completely fine. For our latitude, remember this is cosine. And for our departure, we have sine. So it just means we are typing this into our calculator. We could put our 320.619 degrees in our calculator and hit the cosine function, and that will give us 0.7737. Same thing, we type in sine of 320.6911, and we're given a negative 0.6335. We do that with our BC and our AB as well. Negative 0.4099 and positive 0.2452. Our departure, we have positive 0.09121 and negative 0.9695. Positive and negative is very important here. You can list the positive sign if you want or leave it blank, but just make sure you are keeping track of what is positive and what is negative, because that determines whether we are moving north and south or east and west when we're going around our traverse. Make sure here that you are rounding to 4 decimal places. It will make a huge difference if you round to something less than that. If you're in a spreadsheet, it'll just keep the infinite decimals. That's completely fine. That's the best way. If you're doing it by longhand, make sure that you at least list out the 4 decimal places, if not more. Otherwise, it will make significant changes in your final calculations. Step 6, we need to calculate our latitudes and departures. So here we're looking at our latitudes and departures. We're using our trig functions plus our distances that we took in the field that we found in step 1 that we are going to use for our calculations. So remember, the equation for any given line in our traverse, let's first look at AB latitude, is going to be our distance, 144.05 feet. So if we click over and see, we can have our AB distance, 444.05 feet. That's where the number came from. We multiply that by the latitude of AB. So we simply look back at what our table shows us. So this is negative 4.099, the latitude, cosine for AB. If we do that calculation, we end up with a negative 182.0263, and we can leave it as this, or because it is latitude, we know we're dealing with north-south. Since it's negative, we know that it is going to be south, 182.0263. So you can either write it as negative, or you can write it as south. If we're now looking at our AB departure, it is the same distance that we are dealing with, the 444.05, and we then multiply that by the departure from our table, so 0.9121. That will give us 405.0269. So it's positive, which means we know it's going to be east. Departure deals with east-west. Latitude deals with north-south. So we need to run through all of the calculations for BC and CA. I'm not going to do this on this sample problem, but I will give you the answer so you can check when you're doing yours. So if we're doing our BC, we are going to be using the 333.10 feet. CA will be 129.667 feet in our calculations. And then we will simply use the latitude and departure sine and cosine, depending on which line we are dealing with in our traverse. We run out all of those numbers, AB, BC, and CA, for our latitude and departure. We want to break it up between our north and south, so we know it's positive and negative, as well as our east and our west. AB remember from our previous slide, was a negative, so it's a south 182.0263. The departure was positive, which makes it an east 405.0269. When we run the calculations for the rest of them, BC would be 81.7119 for latitude, and CA would be 100.3288. Departure, your BC is going to be 322.9222. CA will be 82.1442. What this should resemble is our step 5, positive and negative. We had a negative and 2 positive for our latitude, negative, 2 positive. We had a positive and 2 negative for departure, so positive and 2 negative. So they should coincide with one another. Next step, 7, is calculating the linear error of closure. Step 7, calculate linear error of closure, your LEOC. Remember, our equation for LEOC is the square root in the closure of latitude squared plus the closure of departure squared. It's very similar to Pythagorean theorem. So we have our closure of latitude, closure of departure squared, square root of that will give us our LEOC. So figuring out what those closure of latitudes and departures are means we have to go back to the table we just calculated in step 6 and total up all of our north and south and east and west for our entire traverse. For our latitude, our north is 182.0407. South, there's only one number, 182.0263. Our departure, east, one number, 405.0269. And our west is 405.0664. Hopefully the numbers are very close between your north and south and then your east and west. We don't want our closure to be too large, otherwise we'll have a major mistake somewhere in our readings or our calculations. So determine our closure of latitude. We simply take the difference of our north and our south, 182.0407 minus 182.0263.0144, and then the closure of departures is the difference between 405.0269 and 405.0664. Gives us 0.0395. Yes, this should be a negative number, but it does not matter because what we're doing in our LEOC equation is squaring them. So you can think of it as the difference, the absolute value of the difference between the two. So our LEOC is simply the square root of 0.0144 squared plus 0.0395 squared. 0.0420 is our LEOC. Step 8 is calculating the precision. Remember our calculation for precision, LEOC, over our perimeter equals 1 over x. Our perimeter is determined by the 3 distances we measured in step 1. So it's simply adding up our 3 values. So perimeter would be our 444.05 plus our 333.10 and our 129.667. gives us a total of 906.817. We plug that in to our LEOC over perimeter. We have 0.0420 divided by 906.817. Will give us a value of 0.0004632. That is a very long number. All we need to do is inverse. So 1 over 0.0004632 gives us 21,589. So that is our precision. So you're taking 1 over that. So essentially, you can put it in a form where it's 1 to 21,589. But as long as you get your final number here, that is what is the important part. 4 more steps left. Number 9, we're adjusting the latitudes and the departures. So if we look back at our table where we totaled up our latitudes and departures, the north and south and east and west did not add up to be equal. We want these values to be equal, so we need to adjust our numbers here. What we need to make note of is which is the higher versus the lower. So north is the larger number over the south. East-west, our west is the larger number, which means, for example, in departure, if we have a larger number in west, whatever we determine is our adjustment number will need to be subtracted from our larger and added to our lower. So here, north and south, north is larger, so we need to subtract from north and add to south. There is no standard way that it's always one way versus the other. You just need to see what is positive and which one is the larger of the two. So step 9, we're adjusting our latitude and departure. Our equation to do so, for our latitude correction number we're trying to find, it is the distance times our closure in latitude divided by our perimeter. So for each line of our azimuth, it will be a slightly different number. So if we're looking at AB, our distance was 444.05. The closure and latitude number will always be the same. It is our 0.0144. And our perimeter will always be the same number, the 906.817. Gives us a correction number of 0.0700 for AB. So when we're looking at BC, the only number that should change is our distance. So it would be our 333.10. Again, our closure and latitude stays the same. Our perimeter stays the same. And we are left with a correction of 0053. For CA, same thing. What changes is the 129.667 feet times our other divided by our perimeter, 0.0021. So these are all of our correction factors that we will take into account. We're looking for our departure correction. It is the exact same thing, but instead we're going to be using our closure in departure. So we have our distance times our closure in departure all over the perimeter. So for AB, it is our 444.05 times our 0.0395. Our closure and departure is different. Same perimeter though, 906.817. 0.0193 for BC. It is going to be 0.0145. Once you use the 333, the closure and departure and the perimeter, and for CA, you will have 0.0056. So for latitude, we will do our adjusted. So we want to put a table together. We have our AB, our BC, our CA. We've got north and south. Our original numbers we had were 182.0263 for our south, 81.7119 for our north, and 100.3288 for our north. We have to look back and remind ourselves which one was larger. Our latitude north was larger, so we need to subtract our adjustment factors for the north, and we need to add our adjustment factors for the south. We need to subtract from the north and add to the south. So if you just put your pluses and minus in there, then you can go back and see what the actual values are. So for south, AB, 0.0700, BA, 0.0053, and 0.0021, which means our adjusted values then become 81.7066, 100.3267, and we have 182.0334. If we take our 181.7066 and add it to our 100.3267, it will give us 182.0334, which is good because it matches what our north is. If you actually add it up, you'll see that it's 0.333, so it's actually slightly off, but again, this is where rounding to those 4 decimal places will keep you safe. If you rounded shorter than that, your error would be a lot closer to your degree. So we want to make sure that we carry it out as far as possible. Our adjusted departures then. For our A, B, B, C, and CA, we have east and west. Our original numbers, 405.0269. We have 322.9222 and 82.1442. Looking back at our latitude and departure, we have our departure where we had our east was smaller than our west. That means we have to add to our east, subtract from our west. Add to our east, subtract from our west. We've got our signs in place. We can now look at our numbers. We've got 0.0193, 0.0145, and 0.0056. Those come out to be 405.0436, 322.9077, and 82.1385. If we add these two values together, we end up with 405.0462. Again, just one number off, so it is fine. It is acceptable. That is close enough. Step 10, determining the starting coordinate. This is another one where it's nice because it's given to us in our sample problem. So the sample problem tells us that point A, the coordinates are north 5,000, east 10,000. So since it's given, we can just make note of that. North 5,000, east 10,000. Step 11, calculate the coordinates for the rest of the traverse. So we need to find the coordinates for point B and C. We want to make sure that we are using our adjusted latitude and departure. So if we start with point A, our given that we have our north coordinate of 5,000, our east coordinate of 10,000. We then look to our adjusted latitudes. We're going from AB. That means we have a south 182 for our latitude. For our departure, we have an east 405. So when we are looking at this, we need to keep track of our east, west, north, south for positive and negative. Since it is a south for the first latitude, it's going to be a negative 182.0334. For our east-west, it's a positive 405.0463 because it is an east. Latitude was south. So for point B, we have a north 4817.9666, and east we have an east 10405.0463. Our next ones for latitude, we have a north 817066, and we have a west 322.9077. So we have a positive, this is a north, 81.7066. We have a negative 322.9077 because it is a west. So point C becomes north 4899.6733 and an east 1082.1385. We want to run it back to the beginning to make sure that everything is done correctly. So we have a north 100.3267 and a west 82.1385. So it is a positive 100.3267 and a negative 82.141385. It's a west. We use our adjusted numbers. So we return to A at north 5,000 and east 10,000, which is good. Step 12, apply the coordinates to construction. So here we would actually apply this in the field. So there's no calculation related to step 12. We take the coordinates that we have, we plot them on the traverse, and then we can use those to lay out our structure, which will be a separate sample problem. The whole point of trying to figure out these is to figure out what actually our traverse will look like if we don't have a visual already in our head. We always want to start with our crosshairs. That can always help us determine what we are looking at. So we always start going off of our north-south. If we are looking for AB and where that would be, we know it's 114.12. So if we're starting by north, we don't know exactly, but we know it's roughly in our second quadrant because off of north we will go past 90 to figure out where our angle is. When we are dealing with BC, we have 284.12. So if we go around from 90, 180 to 270, we know that it's somewhere in quadrant 4 going in this direction. And lastly, if we are dealing with CA, which is 320, 41.28. Again, it's even further than that 284, so it is somewhere more in this direction, going all the way around to get to 320. So what our traverse then looks like is essentially something that comes down from our A to our B, comes back, we have our point C, and then comes back up to our point A. So our structure would be located somewhere in this traverse. And we have our distances that we calculated as well. So we can use this then to lay out our structure wherever it might be within the traverse.